I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
Space. Time.
the brain,
Life. The universe.
This week, what happens to ships discarded in space? Why do whales sometimes explode? And do giant squid really exist? Yep, it's Q&A time. We're answering your science questions that you've been sending in. I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Let's meet the panel we have assembled for you. Carolyn Crawford is an expert in astronomy and cosmology. She's based at the University of Cambridge. And you have something with you from space, Carolyn.
Yes, something that's come a long way away from space. I've got a little lump of moon rock in my hand.
Good grief, this didn't come from the beach. This is actually the real deal.
Yes. This is the real deal, and it's not like I've stolen one of the Apollo samples. This has actually come to Earth as part of a meteorite. They're very rare, but there are lumps of rock that come from the moon and fall to Earth as meteorites.
How do you know that's from the moon then?
Well, you can look at its chemical composition, its isotope ratios. There are things that you can match it to known samples of Apollo moon rock. This particular one, it's got a lot of sort of calcium. It's got lots of aluminium proportions in, so you can know it's from the moon.
Good grief. Well, thank you very much for bringing that one in. Sitting to Carolyn's right is Duncan Hassel. He's a psychologist and a neuroscientist at Cambridge University, and he looks at memory and video games. And you've brought what looks like a swimming hat with you.
but it's not. It's in a box that looks like it might take chocolates, but sadly for everybody it doesn't. It's a kind of tight-fitting cloth cap that you place on top of a subject, a participant in an experiment, and there are 64 holes in said hat, and within each hole there's a small electrode which has a kind of a small piece of conductive metal in it, usually silver or nickel or something like that, and a wire coming out of each one. These wires are bundled into these connectors which can plug into an amplifier. And this is one of the techniques that we use in my lab to measure electrical activity from the brain by measuring it from people's heads.
So even though that's not in contact with the brain, you can still detect electricity from the brain. Why is that?
In each of these holes, you've got a little electrode, but you can also put in some conductive paste. So you put in the paste and then you use a pointy wooden stick to form a bridge between the person's scalp and the electrode. And so electrical activity, when it's generated by the cortex, by the brain underneath the electrode, will conduct through all the intervening tissues in the scalp and can be recorded by the electrode.
Wow. So you can see which bits of the brain are doing what. Now, sitting next to Duncan is friend of the show, Stuart Higgins. You're a materials scientist.
Yeah, so
Imperial College.
Yeah, so I trained as a physicist. I've now moved into a materials science department. What's caught my eye this week has been a new method for extracting the contents from cells. So a big problem in biology is if you do a study on cells, normally if you want to analyse what's happened to them, you have to kill them and basically put them in a blender and work out what the bits are. What would be really useful is a way of monitoring what's happening to those cells as they continue to live. And this is a great mash of materials science and physics and the same kind of tools used to make electronics, but brought together to allow you to look inside cells as they're living.
Wow. And how does it work?
It's basically like a whole little sheet of straws. So you grow your cell on top of this flat surface. It's got little straws poking out of it. And then what you can do is you can apply an electrical field across it. And if you put electrical fields across a cell, it puts holes into it. So bits of the cell will come out. And those bits of cell will flow through those straws and you can collect them and analyse them. And so long as you don't take too much from the cell should carry on living afterwards.
Goodness. Well, thank you for telling us about that one. I'll bear that in mind next time I want to analyse the contents of a cell. So any questions on materials science and physics, they should go Stuart's way. We also have Danny Green. She's a marine biologist from Anglia Ruskin University. Anything marine biological you'd like to impart, Danny?
I just think if people are going to Google one thing tonight, it should be marine parasites. I think they might be the unsung kind of hero of the marine ecosystem.
Why?
That you wouldn't consider. Just the sheer diversity and the amazing life cycles of them. If you look up tongue parasites, for example, these are isopods that actually take over and remove the tongue of a fish and replace it. And they're really cute. So the fish, when you have the fish has its mouth open, you'll see these little eyes and these little arms.
But can the fish still eat?
Yeah, it can still eat, yeah. So what they do is they'll eat some of the food that the fish eats. And the isopods that become the tongue become female. And if another isopod enters that fish, they enter through the gills. If that fish is already occupied with a female, it will stay as male. and then it will just live inside the fish as well and continue to mate.
Do they mate in the fish's mouth?
Yeah, exactly. They'll mate in the fish's mouth, and then it will just release its eggs, and they have quite a complex life cycle. Everyone should Google tongue parasites.
Sounds like quite a love tangle. Thanks, Danny. Right, one for you to get us started, Stuart.
Is there any technology which can help us run faster or be stronger, like the Iron Man suit?
So that was sent in by Charlie. Stuart, what do you think?
So we're talking about the Iron Man suit from the movies, which is this kind of suit that the character, the superhero can kind of, or maybe not. I'm not sure if Iron Man is a superhero, actually. I think people might argue with me on that. But anyway, you can put on this suit on and can fly around. It gives him extra strength and the ability to do certain things. Now, this is actually a really interesting area of research. People are starting to develop exoskeletons, the idea that you have almost kind of like a powered framework that you can stand into that will support your body as you make certain motions. And there are a couple of reasons for doing this. So some people want to use it in order to help people do lots of repetitive tasks. So if you're a worker in a warehouse and you're lifting boxes every day, moving them around, then this is something that's going to help reduce the strain on certain joints, reduce the strain on your lower back. It's also very useful if you've lost certain mobility, say due to a stroke or something, that it can actually support you and encourage you to do it. There are a few examples around by certain companies. There are still some challenges. So one of the big problems is actually power. I mean, everything comes back down to batteries nowadays. And in order to have motion, you need quite a lot of power and you need a certain battery pack. So that limits the amount of movement you can do at a certain time. Actually, it's quite complicated to replicate the motion of certain joints in the body. So if you've got a ball and socket joint, that motion can be quite difficult to recover in a mechanical system. So how do you design a system that gives you the same range of motion, but then doesn't kind of do things that you don't want it to do as well?
Okay. So is that a thumbs up? It's possible or it isn't possible?
Yep, so it is possible, and they're on the market now. If you have £10,000, you can buy yourself a exoskeleton suit that will allow you to lift boxes more easily.
Karen?
But we're not at the point of flying yet then.
We're not at the point of flying yet. Well, you can get a jetpack. You can get certain jetpacks, and I think there are a few examples recently. My favourite is actually the water jetpack, which still means you need a water supply pumping water down towards the ground, but that does give you kind of those kind of basic capabilities.
Well, thank you for laying that one to rest, Stuart. Danny, let's sort of delve into your domain, which is the oceans. Now, Charlotte wants you to tell her, is there any such thing as a giant squid?
Well, yeah, there is actually. And if you go onto YouTube, you can actually see some footage of the giant squid in its natural habitat. And there was a documentary, I think it was 2013, where they actually went down into a submersible and filmed it in its natural habitat. It wasn't easy to do. They tried all different techniques. They ended up using other squids as bait to lure it in. And it was kind of shimmering in gold. And the professor who's been studying his whole life for this moment was in tears. It was quite beautiful. They thought there were 8 different species, but recent genetic evidence has shown that there's just one species, but they're quite widely distributed globally. They can get to about 14 metres long, but the colossal squid is actually bigger than that, and it's heavier than that as well. And that's mostly confined to Antarctica.
The mantle and the long legs.
Yeah, so that's including that's the mantle and the tentacles as well. So
Still
that's everything,
big.
and it's heavier too.
How much do they weigh?
They estimate that there was one that was 750 kilograms.
Okay.
That's probably the biggest one. There are some people that think that the giant squid, so you've got the colossal squid and the giant squid, both very, very big, both the biggest invertebrates. There's some evidence to suggest that there could be giant squid that are longer than that, up to 20 metres, but it's highly controversial and there's lots of kind of arguments going on about how big they can get.
I found out a really crazy fact that I didn't realise recently, that some squids can change their colour. So is that something the giant squid can do? Can it disguise itself and kind of change the colour of its skin?
Cuttlefish can change their colour very well. I think some squids can, but I'm not sure about the giant squid, actually. I don't know.
They do have a relationship with a bacterium, which is related to the bacteria that give us humans cholera. And they can produce light, and the squid have a certain structure on the skin which they can induce the coloration, so they either feed or don't feed the bacteria, and they can change whether or not they produce light, so they can turn lights on or lights off on demand.
And is that with the deep sea ones
squid.
as well?
I don't know if they're the deep sea
I bet you
species.
people don't even know yet, because we actually know very little about them, because it's a difficult habitat to access and study.
Thanks, Danny. Next up, Carolyn. Stella wants you to sort out some fact from fiction for her on this one.
Are white holes real, and what would happen if one collided with a black hole?
So first of all, what's a white hole? And would there be such a thing as a collision between a white hole and a black hole?
Well, let's start off even with a black hole. Just to remind everyone, that's a region of extreme gravity that comes out of Einstein's equations of general relativity. And one of the really nice mathematical things about these equations is that they're perfectly symmetric. And the same equations that predict a black hole also predict it's like an opposite to a black hole, which is the white hole. So instead of attracting things in, it spits things out. You've got the same mathematical equations. So you end up with the same geometry. You have a singularity. You have what's called the event horizon. In a black hole, it's the point where, once you cross over that, you're sucked into the black hole. With a white hole, you can't return. You get spat out once you cross that event horizon. So far, so good. However, the catch is they're symmetric in time. So time runs forward, you get a black hole. You need to run time backwards to get the white hole. So even though the mathematical equations predict it, we can't actually figure out any way to get a white hole. We see astrophysical black holes on all scales, all through the universe. We see nowhere anything that resembles a white hole. So it is just something that's predicted from the equations. There's no evidence as yet for one existing.
Michio Kaku did a talk here in Cambridge a little while ago to coincide with a book launch he was doing, and his talk was all about parallel universes. And he mentioned something about the idea that you might have a black hole in one universe, and the end of that black hole is a white hole, which is a big bang in a new universe. Could that be possible?
Well, I think once you get to that kind of speculation, anything's possible. I mean, there are ideas that you could have an extreme rotating black hole that smears out the singularity. You could fall into the black hole, perhaps miss the singularity, go through a wormhole, spat out. Ideally, a white hole in our universe, the possibility also could be it creates, a new universe, as you were saying. These are ideas. We still don't know quite how you'd be able to form one, and there's certainly no evidence. And to be honest, if you get spat out in another universe, I'm not sure we're going to know about it in this one.
Well, Andrew Ponson, I think it was on this show, said that with maths you can prove anything you like with theoretical physics. So
that's entirely true.
Everything's up for grabs.
It doesn't necessarily mean something exists.
Absolutely. Thank you, Carolyn. You're listening to The Naked Scientist with me, Chris Smith. Today we're answering the science questions that you've been sending in, and if you'd like to get some questions into programmes like this, send them in now. It's chris@thenakedscientist.com. You can also find us on Facebook or tweet @nakedscientists. Still to come, we're finding out whether Jupiter is gassy all the way through or hard in the middle, and also what's the best way to clean up a beach. Plus, how can you boost your memory? Now, Duncan, we've got this question from Mark here. He says, I'm 53 years old. I've noticed my memory is not as good as it used to be. Is there anything I can do to improve it?
First thing to say is that memory is an incredibly kind of complex phenomenon. Indeed, one of the major roles of the brain is to learn from our experience and our environment and apply that knowledge to new scenarios. But there's been quite a lot of research exploring whether or not you can train people's memories and whether that will yield improvements. So most of that work's been done with short-term memory or working memory. Initially, there were some really exciting findings showing that you could train people's short-term memories, and that would translate to benefits in wider everyday usage. And that spawned a whole series of brain training apps and programs online, which you've probably all seen. However, that finding has been incredibly difficult to replicate.
As in, if you do these things, you will improve your memory or improve your reasoning ability and so on. That sort of finding is hard to replicate. Is that what you're saying?
The original finding that was really exciting was that not only will you get better at the things that you've trained on, that will also generalize to other things that you haven't trained on.
So this is a miracle sales opportunity for the people who make these games, but it's not supported by the science. Ka-ching.
My boss describes it as the Wild West of cognition, in that there are people who make very strong claims about the benefits of this kind of training. But in my view, and I think there's probably the increasing consensus, is that when you look at studies that use the gold standard methods, you can get very strong improvements on specific things that you train on, but you won't get wide generalization.
Is a good way of thinking about this perhaps to say, well, we know the study that was done on the London cab drivers who learned the map of London. We saw that there was evidence of an improvement in the part of the brain, the hippocampus, where you store a map of the world. But we didn't see every part of their brain suddenly becoming a lot larger. We saw just this discrete mapping of the world part of the brain get bigger.
Yeah, so that's quite a nice analogy, a way to think about it. Another way of thinking about it is that the way these training programs work is that they're usually very specific and they're very divorced from reality. So you kind of games online that don't really bear any resemblance to real life. And so one of the big moves in the training field now is to try and develop new ways of training people that are much closer to the things you actually want to improve. So for instance, with the cabbies, they got these specific gains in spatial navigation and spatial memory because they were doing it every single day. And the idea is that if we could design training in a better way that's closer to the things we're trying to help people with, then it might be more beneficial.
So do you think this claim, because patients sometimes say to me, I do the cryptic crossword every day and I know how fast I can complete it in and I've got better and I think this keeps my brain agile into old age. Do you think that's true?
It could be true. It's quite hard to demonstrate empirically because empirically you have to do this very tightly controlled, randomized control trial.
So you think people who can do the crossword, they're in a selection group already.
Exactly right.
They're already pretty good, so they're much less likely to suffer problems.
One of the studies that we have done is with people who've had a stroke. Older adults, usually over 50, and who've had a stroke, and they're experiencing some really quite profound attention and memory problems, which does show that there are some benefits to people like that of current kind of training programs. The pilot study was really quite promising in showing that actually there are people for whom the training could be beneficial.
Well, that solves that one then. Thank you, Duncan. Well, as you know, here on The Naked Scientist, we do like to bust a few myths. We have our regular myth conception. So I thought we'd ask the panel here if you've got any things that you've come across and think that's a real scientific howler. I mean, for me, it would be something like there's this saying that people say, have a stiff drink, it puts hairs on your chest. I mean, that's absolute rubbish because if you do drink too much, it damages your liver and then the amount of female hormones in your body, if you're male, increases, which definitely won't increase the amount of hair on your chest. It will decrease the amount of hair on your chest, which is driven by testosterone. So, Carolyn, have you come across any scientific howlers in your neck of the woods?
Oh, plenty. But the one I've picked up today is that phrase, in space, no one can hear you scream. Now, this is actually right, but perhaps not for the reasons people expect. Because the thing is, sound requires a medium. And so the pet answer is there's no sound in space because space is a vacuum. Actually, there's plenty of sound in space because the space between the stars and even between galaxies isn't a true vacuum.
There's what, 1 atom per cubic metre or something, is it?
I mean, if you think the air in this room, probably the air molecules it occupies 1,000th of the volume. They're separated by, a distance 10 times their size. Once you go out in space, they're separated by, at least 1 million, 10 million times their size. So there's still a medium. It can still transmit sounds. But if you think how a sound works, you have to kind of displace a molecule far enough that it hits another molecule. And it's those vibrations that set up the compressions and the rarefactions that's a sound wave. So in space, you can transmit sounds, but they could have been incredibly long wavelength.
Very, very low frequency, in other words.
Very, very low frequency, yes. So if you could remove your helmet, there are sounds in space, but you wouldn't hear them because they're going to be way out of the sort of 20 to 20,000 hertz that our ears can pick
yes, because
up.
our ears are sensitive from about 50 and upwards to about 15,000 in an adult, aren't they? So under 50 hertz, you're not going to hear it. So you're saying these frequencies would be so low, no chance of hearing them.
That's right. And indeed, one of these sounds I have studied is in an atmosphere that's in a whole cluster of galaxies where the frequency is like one cycle every 10 million years, right?
Goodness.
So that is extreme sound. So there are sounds in space, but it's just such a very different kind of atmosphere that they're not sounds you would hear. So it's correct, but not for the reasons you might think.
Thank you, Carolyn. What about from outer space down at the bottom of the ocean? Have you got any marine biological myths for us, Danny?
Probably just the old sea sirens. So back in the seafaring days in, the 1700s, 1800s, there were lots of sailors that were reporting mermaids. And there are all these, pictures of these beautiful sort of naked women, long flowing hair, luring sailors into the sea. There is actually some truth to that. What they were seeing weren't actually mermaids. They were sea cows. So
dugongs.
Yeah, dugongs, yeah. There's some pictures of these sketches of these mermaids, and you can see that it does look quite a lot like a dugong, except sort of a bit more ladylike, particularly in the bosom department.
A bit of artistic licence.
Yeah, a bit of artistic
licence.
licence. Yeah, so there is some truth for it, which is why they're called sirenia as well, which is sirens of the sea.
Goodness, it must have been a very short-sighted sailor who managed to muddle up a dugong with a mermaid because they
a bit too much rum maybe could have been the case.
Carolyn.
Well, they'd been away from home for a very, very long time.
Exactly.
There is that. Duncan, anything psychological that you'd like to throw into the mix?
So many, it's hard to know which one to choose. So the classic one is you only use 10% of your brain. You use all of your brain. And actually, even the death of cells in relatively restricted parts of the brain can result in quite profound cognitive problems. There are loads. There's like the left hemisphere of your brain is for logic and the right hemisphere is for creativity. That's nonsense. Sometimes people say to me, oh, well, some people's brains are predisposed to learn in different ways. So we have kinesthetic learners and auditory learners. And that, I'm afraid, also is is nonsense.
Dan, you're nodding. Is that
As a
yes because you
lecturer,
are one or because you think this is rubbish?
As a lecturer, we're told that a lot, so we have to obviously account for all different types of learners, and that's one of the things I learned in my PG cert that I did quite recently. And there's 4 different types of learners.
You've just demolished all of
I'm
her
afraid
learning.
to say that.
Well, I do tend to use a lot of visual and and written and all different things anyway, so I think it's okay.
So in that sense, it's great. So what we do know is that if you deliver materials from different perspectives and in different ways, then the learning will be more durable.
Yeah.
We've known that for a long time. That's kind of classic cognitive psychology. But what this is suggesting is something rather different, which is that people, and often children, are predisposed to learn in specific ways and will learn best when information is delivered in their preferred style. And that is not true. And actually, you can demonstrate with the data that children are no better or worse in their preferred style. And potentially, in my experience, actually can be quite damaging. Like if you say to a child, well, you're a kinesthetic learner. Well, then when the lesson is delivered in a different way, they start to think, well, what's the point in me paying attention?
Yeah.
This is not in my preferred style. It's a waste of my time.
It's an excuse to go to sleep in my lectures.
Oh, no one would do that, surely, Danny, I'm sure. Now, Carolyn, we've got a question here from this person who says, Jupiter is referred to as a gas giant. Does this mean it's gas all the way through and you could fly through it, or does it have a rocky middle? How would we know?
Well, this is a very good question because, Jupiter really is giant. It's got a volume which is equivalent to sort of 1,300 Earths. But the fact that it only weighs just over 300 times the mass of the Earth immediately tells you it's mainly made of gas. So it's hydrogen, helium, things like that. That's the predominant component. But we do think there's a rocky core, and maybe a rocky core that could be 10, maybe even up to 30 times the mass of the Earth, all compressed down into something slightly less than the size of the Earth, right down under all that atmosphere. And we can't fly through and find out. This is an experiment you can do because the trouble is, if you throw a spacecraft into Jupiter, which we have done, by the way, enter the Galileo mission, spacecraft goes into Jupiter, a good way to dispose of a spacecraft at the end of its mission.
Because Schumacher Levy 9 plunged into Jupiter as well, didn't it?
What happens is, when you look at the disk of Jupiter, all you're seeing are the cloud tops, just in the first few hundred kilometres. The gas is molecular for about 1,000 kilometres in, but after that it has to carry the weight of all the overlying layers of gas, and it starts to get high temperature, high pressure, and it becomes as incompressible as a liquid. So if you throw any spacecraft in, it's just going to get crushed, it's going to get destroyed really quickly. So we can't fly in and find the rocky core or see it. We think it's there from everything we understand about how planets form. We think you have to have a rocky core that grows quickly that can then sweep up the gas and accumulate this huge atmosphere. But the question is, how do we measure its size? How do we measure its mass? And this is in fact what we're doing now with the Juno spacecraft that's in orbit around Jupiter. And it's got this 53-day orbit. On one end of the orbit, it skirts to within about 4,000 kilometres of the cloud tops of Jupiter. And as it does that, it's tracking the form of Jupiter's gravitational field, which of course depends on the distribution of mass within the planet. So that's our way of tracking it. And that's one of the main things the spacecraft, it's got a lot of other science, but one of the main things it's trying to determine. And Danny was saying, if you Google one thing tonight, go and do tongue parasites. Well, that doesn't quite appeal to me, especially when I'm having my dinner. But I would say, go and Google Juno, NASA Juno mission. They've put up just in the last week some fantastic images from some of these flypaths of Jupiter, and they're just beautiful, as well as being really interesting science, but just mesmerising.
Duncan?
If there is a rocky core, is there any way of knowing what the rocky core is made of?
Well, it's the same as all the rocky planets. So it's going to be carbon, nitrogen, oxygen. You've got magnesium, you've got silicon, you've got iron, all the normal things that make up all the rocky planets. It's just that when Jupiter forms, it forms further out from the sun, and you've got all these volatile ices and molecules. That rocky core can then sweep up those and accumulate in an atmosphere in a way that the planets like Earth and Mars can't, because they haven't got all those lightweight gases around.
We'll just sneak this one in very quickly, Stuart. This is a question for you from Katie.
What's the smallest particle we can detect? And how small is it?
So what's the smallest particle and how small?
Do you know what? It's a really difficult question to answer. I had to go back to my particle physics undergraduate notes to check. It's very difficult because in our current understanding of physics, the standard model of particle physics, we treat the fundamental elementary particles as point-like. That means they don't really have a size. And that kind of causes the whole issue of problems, both conceptually and also potentially mathematically. But what we can think of, though, in terms of these particles is actually what kind of size do they interact over? So if we were to fire one particle into another, what's the kind of area that they would interact with? And that's called a cross-section in particle physics. And in that case, something like a quark, which is the constituent of a proton or a neutron, very, very, very tiny. I'm going to quote John Butterworth, who's a professor from UCL, who said it's about 43 billion billionths of a centimetre. So absolutely incredibly tiny. That's the upper limit it could be. So it could even be smaller, or it may not even have a size at all.
So there you go, Katie. The answer is pretty small. You're listening to The Naked Scientists with me, Chris Smith. And I'm joined by some of our friendly neighbourhood scientists who are ready to take on your science questions. With me are astronomer Carolyn Crawford, physicist Stuart Higgins, marine biologist Danielle Green, and psychologist Duncan Assel. On the way, we'll find out the best way to clean up a beach and whether stars can glow green. But before we get stuck into those, it's time for our fiendish quiz for our panel and for you at home. We're going to have two teams. So what we'll do is we'll have Danny and Stuart, who are sitting next to each other. You'll be one team, and we'll have Carolyn and Duncan as the other team. So I read you a question, obviously, and you have to decide if it's right or if it's wrong. If it's right, you get a... and if it's wrong, then you get a... So here we go. It's going to be best of three, basically, but it'll be pretty obvious if someone gets there first. So Duncan and Carolyn, this is your first question, and you can confer, of course. So a bit of jolly conferring is fine. What's got more eyes, a dragonfly or a box jellyfish? What do you think?
Dragonflies only got two eyes, but they're these really sort of compound eyes, though, aren't they? Do they count as individual
I don't know.
eyes?
My knowledge of eyes is limited.
And this is very embarrassing because I do have a son who actually works on insect eyes, so I should know the answer to this. Do jellyfish have eyes?
I don't.
I'll have to push you.
I think dragonfly.
Okay, well, if you can count all those sort of little compound bits as eyes, I'd go with dragonfly as well. We're wrong.
I'm sorry. Actually, dragonflies have two eyes, and we acknowledge they are compound eyes, so they're built from tens of thousands of miniature units. But the box jellyfish, in terms of physical eyes, has actually got 24 different kinds. So the box jellyfish has more eyes. Did you know that, Danny?
I might have been thrown, to be honest, by the
woods.
complex eyes as well. I could have been a little bit thrown, but yeah.
Yeah,
I probably would have erred on the side of the jellyfish.
Discovered in 1955, Chironex fleckeri, after the doctor who fished one out of the water because a young boy unfortunately died of the sting, and he was found to have found a new species of jellyfish, and it was named Chironex fleckeri in his honour. Right, 0 for that, so you're doing well so far. Let's go over to Danny and Stuart. Who holds the record for smallest vertebrate animal with a backbone in the animal kingdom? Is this a fish or is it a frog?
I'm looking at you here, Danny. So the smallest...
I'd be tempted to go fish. I don't know.
If I think...
To be honest, I don't know.
I can imagine a fish being smaller than the smallest
Yeah.
frog I can imagine. What do you reckon?
Let's go fish.
Okay, we're going to go fish.
No, it's actually a frog is the answer, but only
Which one?
recently. The record holder until 2012 was an Indonesian fish, Pedicipris progenetica, and that was just under a centimetre long. But then a frog came along, which is Pediphrine amanuensis, which was found in Papua New Guinea. It's just 7 millimetres long, this frog. Isn't that tiny? And there may actually be smaller vertebrates to find, but they're much harder to spot, so no one's actually seen those yet. Right, okay, we're level pegging, very high scoring round so far, 0-0. Back to our first team, Duncan and Carolyn. What would take longer, walking once around the equator of Earth or taking a space ride to Mars?
Well, it depends how fast you travel through space, doesn't it? If you could travel at the speed of light, you'd get to Mars a lot quicker than if it take you to walk around.
Do you mean kind of with standard space travel methods?
No, don't qualify it. In a rocket, it takes you 6 to 9 months to get to Mars. And you could also say that it depends whether we're on the same side of the sun as Mars at the time or not.
Oh, gosh, it's complicated.
Yeah, it's a kind of three-dimensional problem, isn't it?
Let's say it's 6 to 9 months to Mars from here.
Yeah, by a conventional spacecraft.
Exactly. I didn't know that I could walk around the equator of the Earth.
I think it would be a challenge, yes.
In 6 to 9 months.
So what are you going for?
Should we say it's longer to walk around the equator?
Yeah.
Especially difficult over the sea, wouldn't it?
You're going for it's taking longer to walk around the equator.
Yeah.
Yep, you are right. Okay, we have done a few back-of-the-envelope calculations. The equator is around 25,000 miles around, and so if average walking speed is 3 miles an hour, that would take you 8,300 hours to walk around it. Now, assuming that you don't need any breaks and you can walk through water, few assumptions there, it would take about 345 days to walk right around the equator. On the other hand, spaceships have got to Mars in 156 days, so it is actually quicker to get to Mars. Very well done. 1 point, Duncan and Carolyn. Right, okay, Danny and Stuart, here we go. Which is larger, the number of germs in a sneeze or the number of trees on Earth? What do you think?
Oh, blimey. Oh, there's a lot of trees.
Yeah, but microbes are really small, aren't they?
Yeah.
You know all about size, don't you? You're the size
cells,
man.
yeah, I suppose cells are on the order of about 2 microns, so 2,000ths of a
And like
a
if you, the
millimetre.
volume of a
Yeah.
sneeze, so like a litre, is it that much?
A litre of
No,
sneeze.
I've
Oh,
got
that's
hay
horrible.
fever.
Oh.
It feels like a litre today.
But there's all that business. If you sneeze in a tube carriage, it kind of
Yeah.
hits the back end of the tube carriage. Like you
Yeah.
go all through the train
Okay,
carriage.
well, on that pleasant
It's
thought, would you
speed,
like to
isn't
give
it?
me an answer? Are you going more germs or more trees?
More germs.
They're teensy, aren't they?
Yeah, let's
we'll
let's
go
smaller.
germs.
Go germs.
I'm afraid not. It's trees. There are thousands to millions of virus particles in an infected person's sneeze, but a recent estimate by researchers at Yale University put the number of trees on Earth at about 3 trillion. Would you believe? Absolutely amazing, isn't it? Although the number is going down, they caution. They say we're losing trees. Okay, right. We might as well carry on. You might as well have the last one. What releases more carbon dioxide? One human breath or running a Google search? Duncan and Carolyn.
Yeah, because a Google search doesn't last very long.
I'm just trying to think as to how to quantify the amount of carbon released from a Google search.
Well, presumably the computers that are running or what you need to have.
The electricity.
Yeah, electricity and what you maybe need to have manufactured to enable that Google search. Should we be controversial and go for the Google search?
I'll trust you.
Oh, don't.
So you're going for Google releases more CO2?
Yeah.
Yeah. According to Google's own numbers, a typical Google search amounts to 0.0003 kilowatt hours of energy. You would need to emit about 0.2 grams of carbon dioxide to generate that as electrical power to run the Google data center. The average human, on the other hand, exhales around 1 kilogram of carbon dioxide every day. So at 12 breaths a minute, that's roughly 0.05 grams of CO2 in every breath. So Google searches cost more CO2 than a human breath, but the figure is a little tiny bit controversial because Google's figures don't include the carbon cost of running your own computer, which would, of course, change the equation a little tiny bit. So could be a tie up here. Right, are you ready, Danny and Stuart? What kills more people, sharks or selfies? Sharks or selfies?
Oh, my goodness.
I mean, I want to go selfies on that.
I mean, I want to, yeah.
Just because people like off the side of cliffs and things, isn't it?
A big thing recently, and like governments have started warning people
Yeah.
to stop taking selfies
There's
off
signs up
dangerous
now with
ledges and things.
Like
yeah.
with a person with a selfie stick and it has a red thing through it. There's like signs telling people not to in dangerous places.
It's got to be selfies, right?
So yeah, let's go selfies.
Okay, going selfies. It is indeed selfies. Sharks kill around 5 people a year, but in 2016, over 50 people were killed off taking photos of themselves on their phones. I say that's Darwinian evolution, but that's just my feeling. That means we have a tie. So it's now tie.
Tie.
No, you got one, didn't you? Oh, no, you got Google right. You got the Google search right. Sorry, we don't have a tie. So the winners this week with a prize beyond price, the prestige of winning the Naked Scientist Fact or Fiction quiz this week, it is Duncan and Carolyn. Very well done. Now, Carolyn, we've got this question, which is probably one for you.
Can you get green stars?
Well, this is a very interesting question because some people are always amazed to know that stars have colours. Because if you stand out in your back garden, you look with your unaided eye, they all look white. Except one or two, like Betelgeuse, maybe look vaguely orange. Now, if you look through a telescope, you begin to see a few more colours. And obviously, if you have pictures taken with a digital camera, those colours begin to pop out. You see there are blue stars and yellow stars and red stars and white stars. But yet, curiously, there aren't any green stars. And the colour of stars is related to their temperatures. So in the same way that if you heat a lump of metal up, it starts glowing this sort of very dull red, it goes through to orange. At its hottest, a bright, almost like blue-white. The same with stars. They are glowing because they're hot. It's thermal radiation. And in physics, unlike your plumbing, red is cool and blue is hot. But if you could analyse the spectrum, in other words, you look at the distribution of light given off by stars, they're not just giving off that one colour, they're giving off in a whole range of colours. It's called something called the black body radiation. And if you could map it out, it would look like a spread of all colours, but with a definite peak. So a cool star, that peak is in the red, so the red light dominates. And as the star heats up, that peak shifts through to the blue. So if you get a star at 3,000 degrees, it's very cool and red. At 30,000 degrees, it's stonkingly blue. Now, what is curious is if you get a star like our sun at about 6,000 degrees, that peak is bang in the middle of the visible spectrum. Now, the difference is you've got that peak, that's where most of the light comes out. But if you're right in the middle of the spectrum, you've got as much yellow light and as much blue light to either side. So your eye kind of mixes it together and sees it's white. But if that peak is at one end, so either at the red or the blue, you're just seeing that peak and one side of the colour. So you don't get so much mixing. So even though our sun predominantly gives off most of its light green, we got all this yellow and blue next to it and it gets mixed out as white.
Danny?
I was just going to ask, does the colour give any indication and does the temperature give any indication of the lifespan? Are the really hot ones about to explode or is it not as simple as that? You can't?
Well, it is very, very clever because the temperature tells you how hot the star is, which in turn tells you how massive the star is and also how old it is. And you think we learn all this just from taking spectra or images of stars. We can work out all these things. And it's kind of perverse because if you have a really hot star, it has to burn energy at such a rate because it's a really massive star. So a star's life is just basically a battle against gravity. So if you have a really massive star, it's got to burn that much hotter. It's got to go through its fuel that much quicker to, withstand gravity. However, even though it's a bigger star, it goes through its fuel faster and so it has a shorter life. So if you see a bright blue star, it's a really young star and it's a really massive star. And if you see a very cool, dim red star, that's actually going to have a lifespan of billions of years, unlike the hot blue star, which is perhaps millions of years. So you can learn an awful lot from the colour.
Thank you very much. Now, let's think about the human brain again. Duncan, we've got a question here which says, is it actually true that women are better at multitasking than men? And is it possible to improve your multitasking ability?
The bottom line, really, with any kind of cognitive task is the more you practice it, the better you get. And so I see no reason that would be different with multitasking, that you can train it, that people will get better at multitasking. Whenever I give a talk, people often ask about gender differences. In any of our data sets, we tend to find that there are very, very few gender differences. And there are, as far as I know, there are no gender differences in multitasking.
Where does this idea come from? Because it's very pervasive. It's commonly said.
There are all sorts of gender stereotypes that are incredibly pervasive. So actually, in 2014, there was a paper in Proceedings of the National Academy of Sciences where they scanned the brains of 500 men and 500 women, and they used a type of science called network science, which is looking at how different areas of the brain are organized and how they're connected with each other. And they identified some differences between the two groups, between the genders. And on that basis, they said, well, that must be why women are such good social communicators, where men are really good at sort of perception and action tasks. And of course, they didn't have any data to suggest that actually that was true. And there's actually a real risk that whenever you identify any differences in the brain, that you use that to kind of peddle some kind of gender stereotype. It's like me saying, I've surveyed everyone in this room and the men on average are 10 centimetres taller. That must be why men are such great leaders. Well, we've got no evidence that that's true anyway. So I think that's often why these things become so pervasive, because actually it's just a way of peddling well-entrenched stereotypes.
So beware of the stereotype. And therefore, is there actually any way of getting better at multitasking if you're not good at it to start with? Are there various techniques that one can employ to improve?
Well, I've never tried it, but the bottom line with cognition is that practice makes perfect. So you get a really massive practice effect, even on very complicated tasks. Whether it generalizes to other sorts of multitasking is a bit of a grey area.
I will bear that in mind while I'm bearing lots of other things in mind. Hopefully I'll get better. Now, Danny, let's head out to the beach because we've actually heard from Justin, who says he wants to know how he should go about perhaps cleaning up his local beach. He said, would putting something like phytoplankton in the water be helpful, or some seagrass or some eelgrass, or planting some algae? What would you recommend about beach cleanup?
I think the first place you could start is to get involved with a local kind of coast watch, litter watch group and go out and collect litter, collect marine anthropogenic debris. So most of that will be plastic. In terms of beach regeneration and replanting, of angiosperms and algae and things like that. It's a lot more complicated and difficult. And there's been a lot of work done on this. I'm assuming that the beach he's talking about used to have seagrass in the first place, because if it didn't, then you shouldn't really go in and mess with a habitat. It is what it is. If it's a sandy beach, it's a sandy beach. If it doesn't have seagrass on it, that's fine. But a lot of the seagrass beds have been destroyed by people, and the quality of these habitats have been degraded, and they're really important nursery grounds. They're really important for ecosystem services, ecosystem functioning. So if, in terms of restoration, there's a meta-analysis about this recently that have found that the most important thing you can do with restoration of seagrass habitats is to make sure that the habitat is in a good state already. So that's in making sure there's not a lot of litter and other pollutants. So you clean it up first, and then you replant. And you want to replant in quite a big quantity. So I'm not sure that one person on their own could do this. This is something that you need a whole team to do. They found that the larger quantity that you replant, if you also replant with a lot of genetic diversity, then you've got a greater chance of the survival of the shoots, increased productivity, biomass, and healthier seagrass.
There was a paper came out quite recently showing that if you have these seagrasses, they seem to have some kind of sterilising effect on the water in terms of pathogen sterilisation. They remove bacteria which we would regard as harmful, as pathogens, from the water, and the levels of these pathogens in areas where there were no seagrasses were perhaps an order of magnitude higher.
Oh, okay. I've not actually seen that. I wonder if that's because of the microbial communities on the actual seagrass itself.
Yeah, they said they don't know, and they speculate that it appears that perhaps the microbiome on the plant is influencing things, or that the other species which are attracted to live in the seagrasses themselves have some kind of antimicrobial, antipathogen effect.
And in the sediment beneath the seagrass as well, because they actually are one of the few kind of marine plants that are going to create a complex habitat beneath the surface of the sediment too.
But the bottom line is, if we mess the environment up, we do so at our peril, and we probably need to be a lot more careful about better stewardship of our planet, don't we, really? That's the bottom line.
Yeah, that's definitely true. And I think it's very good that people are asking these questions too.
You're listening to The Naked Scientist with me, Chris Smith. And if you'd like to get a question in, remember it's chris@thenakedscientist.com or tweet @nakedscientist. Now, Stuart, here's one for you, and it's from Tony.
What happens to old spacecrafts?
So what happens to knackered old spacecraft once we've done with them?
So it depends. If we're talking about spacecraft such as satellites, then you've got a couple of choices. You can do the fun thing, which is we talked a little bit about earlier, which is to dive them back into a planet or into a star. And so you can bring them back into the Earth's atmosphere, and most of the time, the majority of the satellite will break up in the atmosphere as it burns up and gets very hot. If you're a bit unlucky, maybe a few fragments will make it back down to the ground. The other option is to stick it into what's called a graveyard orbit. So you can put them about 200 miles higher up than the active satellite, so about 22,400 miles above the Earth. And the idea is basically put them out of the way. And this is a really big problem, because actually we've got starting to put so many satellites into space, so many satellites orbiting the Earth, that all that rubbish is starting to get in the way. And because these things are moving so quickly and so fast, the impact of these parts of debris of systems can cause huge problems with existing and active satellites that are out there. So it's something you really have to take care of nowadays.
Because the particles are whizzing round at ludicrously high speeds and energies, aren't they? So if you happen to be on a spacewalk or something, it could tear through your spacesuit, it could tear through your spacecraft.
Yeah, it's a huge danger to the International Space Station if you've got a small millimetre-sized particle doing 1,000 kilometres an hour that can go through a side of shielding or something. That's a big problem. Yeah.
Even faster than that in some cases, isn't it, Carolyn? Some of these particles are moving very fast.
I mean, the space station itself is going about sort of 8 kilometres a second, phenomenal speed. I will just say, though, the space station's actually quite a relatively low Earth orbit. So anything that's orbiting at that height, if it's not being continually boosted, will decay and burn up. One of the most recent examples was the astronaut who let go of her toolkit by accident, and it drifted away from the space station. And I can't remember how many weeks later, people could actually see her toolkit burn up in space because the orbiter decayed and then it reached the atmosphere. At the height of the International Space Station, there is junk around and you're relatively safe. But further up, we're just getting cluttered. And you have the immense danger of things colliding. You get this sort of breakaway thing where you have these high impact collisions, bits fly off that are more likely to impact other satellites, and it could be disastrous.
The height of the International Space Station is 150 kilometres or so up, isn't it? Something like that. It's not very high.
A bit higher than that, probably about sort of more 350, 400 kilometres. Space starts at about 100 kilometres, roughly.
Every time a supply ship comes up, it docks at the International Space Station. They allow it to boost it a little bit higher to stop it coming back into the Earth's atmosphere.
Gives a bit of momentum to speed it up
just a little
again.
push.
And moving on now, here's one for you, Danny.
Why do beach whales sometimes explode? And what are they doing on the beach in the first place?
Indeed.
Okay, the reason that they explode, and actually they don't explode as often as people think that they do. There's been some horrendously documented cases of it on YouTube, because it does happen, unfortunately, sometimes. Basically, the microbes in their bodies and their guts still are degrading them, and this is releasing gas, and they've got very thick skin, so that this gas isn't easily released from the body, so they will bloat up, and sometimes they can explode. Sometimes they explode because people are jumping on them. So never a wise thing to do, not a good idea. What are they doing on the beach in the first place? Whale strandings are quite a common phenomenon. I feel like I can never say that. Can someone else say that word for me?
Phenomenon.
Thank you. And there's a lot of evidence to suggest different theories. So there are natural things that can lead to this, so disturbances in the weather. Sometimes smaller whales, like pilot whales, will be herded in by large predatory whales like killer whales, and they'll end up being stranded on the beach. Unfortunately, there's quite a bit of recent evidence to suggest that it's anthropogenic noise, so that's noise made by people. The oceans are an extremely noisy place anyway, but there's a lot of evidence that sonar from military operations is actually affecting the navigation systems, because the whales use echolocation. And there's correlations between them coming up from the deep too quickly and developing decompression sickness as well. Can get hemorrhaging from really loud noises. So some of the noises used by military and other sort of boats are extremely loud, hundreds of decibels, and they can actually get hemorrhaging in their ears, and they use their ears to echolocate. So this can put them off kilter and they'll become stranded. So there's quite a lot of evidence that human noise could be an issue as well, but there are natural reasons too.
Weren't you saying something, Duncan, about people actually dynamiting these whales? Or not before they're dead, obviously, but when they're on the beach to get rid of them and clear up the mess?
Well, that is what I naively believed. So before you just gave that answer, I said, well, it's just an efficient way of disposing of a very large whale. Just kind of blow it up, and then, seabirds and so on will eat it.
Because that would make quite a stink.
I've never heard that, but I wouldn't be surprised.
Well, that is just what I thought was true. I've got no evidence to base it on whatsoever, and I'm so glad that you've put me straight.
The humble microbe strikes again, I think.
I think, actually, taking a historical perspective for a minute, Henry VIII wasn't quite whale size, but he was getting there towards the end of his life, and I think it was a very hot day when he died, and the history books, I think, will bear me out on this. He did explode for a very similar reason. As you say, he fermented internally, and there was a pocket of gas that built up, and then Henry VIII was no more. Back into space, John would like to know, Carolyn, the sun rotates on its own axis, does it? How do we know that, since it's a ball of fire?
Well, yes, it does rotate. It rotates around an upright axis about once every 4 weeks. And the first person to realise this was Galileo, because how you know something rotates is you look at a fixed feature on its surface and you wait. You time how long it takes for that feature to come back into field of view. Now, normally, when you look at the sun, and this is not a recommended practice, I hasten to add, there are no features. But he used his telescope to project images of the sun, and he saw sunspots for the first time. And these are just like little black specks on the disk. Well, little. They're they're bigger than the size of the Earth. They're tens of thousands of kilometres across. They just look tiny on the surface of the sun. And these are slightly cooler, they're slightly darker, and they rotate with the sun. And so he tracked how those progressed across the disk of the sun and worked out the sun rotated about every 4 weeks. However, it isn't a solid body. So even though the sun rotates, it's not like a planet where every bit on the surface rotates at the same rate. And in fact, the sun shows something called differential rotation. Indeed, this is why we know it's made of plasma rather than a solid thing. The sun rotates unevenly and it changes with the latitude. And at the poles, it takes 10 days longer than it takes at the equator.
Does that mean it tangles itself up almost? It sort of screws itself up like winding up an elastic band because there is this differential effect?
Yes, and it is really crucial for magnetic fields because a lot of the sun's activity is driven by magnetic activity. So not only do you have convection currents underneath the sun, you've also got this differential rotation and you get this kinking and this knotting of magnetic fields, and that stores up magnetic energy and that will suddenly be released. And that is part of, obviously that's to do with sunspots and how they're created, but also these enormous solar explosions that get generated. It's from those magnetic fields reconnecting back after exactly that tangling and releasing this huge amount of energy.
Is that the coronal mass ejections, CME events that David Willits had a space weather forecasting system he set up in the UK to spot that?
And we should be very worried about them. I mean, this is one reason why we have so many satellites that are trying to understand the sun, trying to be able to predict these events, because they do have potentially catastrophic implications.
Let's hope there's not one coming too soon. Now, Duncan, I want to sneak this one in because Charmaine's been in touch and wants to know the best way to study for exams. There must be lots and lots of people who are studying for exams at the moment, so this is a very important question. What do you think?
3 tips that I can bring to mind. Number 1 is sleep. Make sure that you get plenty of sleep. So when we're sleeping, when we're offline, during non-dreaming sleep, so non-REM sleep, you undergo a really important process of consolidation. So where you integrate new information with your existing body of information. And that results in kind of durable, solid memories. So get plenty of good quality sleep. Number 2, there's this really famous effect in psychology called spaced versus massed practice, which is that if you break the learning up over multiple sessions rather than bunching it all together, you get an added benefit. And that's because each time you revisit the information, the very process of retrieving the information again strengthens its trace and results in more durable memories.
So, sorry to interrupt, are you saying that basically I should make myself a revision timetable, identify basically what I want to learn, and then start each session by revisiting the things I've learned before? Or are you saying that basically just by breaking up and not trying to do too much at once, you give yourself some mental rest, if you like?
Yeah, so when you put your revision timetable together, rather than, say, planning an entire day on one particular topic, space that topic out across multiple days. And that's a better way of structuring the learning. And the third thing is to test yourself regularly. So we know from cognitive psychology that much as it's unpopular, but testing for learning is a really beneficial thing. So
isn't that what the exam is for?
Well, that's like a one-off thing, right? But if you could incorporate testing, not for the purpose of necessarily seeing how good you are, but you actually learn very well when you incorporate testing with the revision.
Some brilliant tips there. Thank you very much, Duncan. Can you sneak this one in quickly for us, please, Danny? And you've got about a minute and a half to do it. We keep hearing how smart dolphins are. Have we ever been able to communicate with them in a meaningful way?
Well, so I've only got a minute. There was a...
Well, you haven't. Yeah, you did have a minute and a half.
There was a professor. Okay. There was a professor in the 1960s called John Lilly who tried to do this, and he did this he's the inventor of the that incubation thing that people lie in. I can't remember what it's called now. But anyway, he actually got his research assistant to cohabit with a dolphin. So she shared her space with a dolphin for about 6 weeks. The house was half flooded. So she slept on a bed of salt water. She lived, she slept, she played with the dolphin. His name was Peter. Very controversial experiment. You wouldn't get away with it these days. He had this theory that they'd be able to communicate with each other. They'd speak each other's language. He even dosed it up with LSD. Unsurprisingly, he didn't get his funding renewed.
He just believed he did because he was so spaced out.
He wrote quite a few papers about it. There's a science paper about it in 1961. He thought that we could communicate, but more recently they've developed a device. They're developing a device, interspecies communication, and it's called CHAT, which is cetacean human auditory something or other, telemetry, I think. And this is meant to facilitate communication between humans and dolphins, but of course it's not proven at all that it will work.
Well, well done, Danny, for managing to answer that in super fast time. I'm sorry to say, on the subject of time, we have run out of time. Thank you very much to our guests. We were joined by Danny Green, Duncan Assel, Stuart Higgins and Carolyn Crawford. It's been a pleasure to have you. Thank you for production to Georgia Mills and Katie Hayler. Next week's show is all about your ticker. We're off to the British Cardiovascular Society meeting to find out about your heart and how it performs in extreme situations. The Naked Scientist is brought to you from Cambridge University and supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith, and thank you very much for listening. Until next time, goodbye.